Okay. Let's get started. So uh, now we have only one last event, the final exam for this semester, right? Because we had the campus festival in the last week. So for this semester, we have only one event. Okay, so final. So let's study hard until the final, the last day of the this semester. Okay. So we learned about the arithmetic unit in this system. So I explained that arithmetic units are the digital modules required for performing arithmetic operation. Then, as I mentioned, actually many computer instructions are arithmetic instructions. So it means that actually the computers receive number data. So number data is the binary data, and then using these binary data, the computers perform arithmetic operations or logical operations. So computers have computers perform many other kind of instructions such as the branch or load store instructions. But actually, using data, the computers perform arithmetic or logical instructions. So it means that these arithmetic units, such as such as the adder, or divider, or subtractor, and multiplication. So these arithmetic units are basic units for computer processors. Okay, so that's why we are learning about the arithmetic units in the logic, this digital logic design course. Okay, so in the previous class, we learned about the half adders and full adders, and then I believe you can understand the half adders or full adders without any trouble, because this is very simple, and I believe you can understand the behavior, and then is that the binary operations of half adders and full adders, right? So we can just define the input and output of half adder or full adder blocks. Okay, so we can define the output sum and carry it out like this. Then we can generate the Boolean equations. Boolean equations for half adder and full adder. And then actually, so we also learn how to perform the add operations for the binary data. And then which means that, so actually, so which is, the carries are propagated from LSB to MSB. So which means that by combining full adders, so which means that we can, so the carry out of the previous digit is connected to the carry in of the next digit. So this is the referred carry adder. So by combining full adders, then we can build the multi-bit adders. And then I mentioned that usually the computer processors handle 32-bit or 64-bit integer data. So for the integer operation, the computer processors handle 32-bit, usually the old generation computers. And then nowadays the computer processors handle 64-bit integer data. So it means that in our computer processor, so we require 64-bit integer adder. It's a 64-bit. Then what's the problem? If we implement the 64-bit adder using this referred carry adder, the problem is delay, right? So also in the previous lecture, we learned that the delay of combinational logic besides the clock frequency, right? The clock frequency. And then everyone wants fast processors. So which means that if we use slow clock, then and the performance may be low. So we need to reduce the delay of multi-bit adder. Then the critical path for this ripple carry adder is the carry propagation. So carry is propagated from the LSB, the first carry input to the last carry output. And also, in order to generate this the last some bit, then the carry is propagated from the LSB to the MSB. So because the carry is propagated, and this adder is called ripple. So ripple means it's kind of it's a wave when they form a wave. So this adder is called the ripple carry adder. And then I mentioned that the delay of ripple carry adder is proportional to the number of bits, because the delay of is ripple carry adder is the same to the delay of this carry out, then is multiplied by number of bits, right? So it's linearly proportional to the number of bits for the ripple carry adder. But we want reduce this delay of adder. Also, the adder is the basic module for implementing other arithmetic units, such as multiplication or division unit, right? So I will explain later about some multiplication or division in the computer processor, but so actually, when we learned about the basic arithmetic operations in elementary school, so we already know that the addition or subtractions is easier, so much easier than multiplication or division. Why? The multiplication is composed of many addition, right? Because we need to generate the partial product, and then for this partial product, we need to perform add operations, right? And also division. So for division, then we just perform repetitive subtraction, right? So actually, in computer processor, computer arithmetic engine, addition is the basic operation for the arithmetic unit. So that's why we are learning about the add implementation more thoroughly. Okay, so now we will learn about the carry Lookahead adder. Then I also explain the definition of Lookahead. So Lookahead means that it think about what will happen. So it means that we think about the future event earlier. So actually proactively. So that is the definition of Lookahead. So Lookahead adder means that actually what is the future event for this ripple carry adder. So if we just consider the delay of this ripple carry adder, the future event is the sum output of the MSB. And then in order to calculate this S31, right? S31 of S31, then we require actually 330. Okay, that is the carry out of this 30 bit number 30. So if we can calculate, if we can know the value of the T30 earlier, right? Then we can reduce the total delay of this multi-bit adder, right? So that is we need to calculate carry earlier. Then how? It's important. how can we calculate the carry earlier? So let's see the detail. So let's review the operation of full adder. So as you can see, you can find that the full adder has two inputs, A and B, and then this is carry. It's a carry in. And then by combining these two inputs, A and B, and then carry in input, that you can generate the S and C out. But let's ignore this carry in. So which means that let us assume that we don't know the. Okay. So we don't let us assume that we don't know this value, the exact value of the C in. We don't know about this full adder, but even though the C in, we don't know the value of the C in, then we can expect, we can know how the C out will be 1. So will be 1. So will be 1 regardless of the value of C in. We can know if we just we just check the values of A and B, then we can know the carry out can be generated. So it means that the carry out will be 1 regardless of the value of C in. Which cases? If A is 1 and B is 1, then in this case, the carry out will be 1 always, right? Because it's obvious, right? The one is A is 1 and B is 1, then regardless of the value of C in, the C out is always 1. Okay, so we can say that this is the generation of carry by these two inputs, A and B. And then we can also assume some cases that propagate the carry in into carry out. What cases? If A is 1 or B is 1, right? Then if the carry is 1, then this carry is just propagated to this carry out. So we can distinguish the carry out event only considering the inputs A and B. Just ignore the carry in because this carry propagation is the main source of the long delay of this ripple carrier. So we just consider that. We just check the A and B event, then we can define the carry generation event, then carry propagation event by its A and B. So we can define like this. So the generation for each column, what is B, what is digit of this add operation. So this is I, the I speed. Then we can define the generate operation, and then propagate operation like this. So this is the generation means that the carry will be generated regardless of the carry in. So it means that the carry will be always 1. Okay, so we can define the GI for each I speed like the AI and GI. This is the generate signal. And then propagate. So as I mentioned, the AI is 1 or so is or then BI. Then the carry in signal for this 4 adder will be propagated, right? So we can define the generation signal and propagation signal like this for each digit. Okay, digit Gi and Pi. Then how we can calculate the carry out like this? So actually, it's the same. It's the same for the it's the same to this Boolean equation actually, right? So if you see the Boolean equation of this full adder, so this is the Boolean equation of the full adder for C out. So you know the C out is the AB plus AC in plus BC in. And then using the carry generation and then carry propagation signal for each digit I, then we can define the carry out like this one using the generate signal and then propagation signal. So it's a GI plus PI and CI minus 1. CI minus 1 is the carry in for this digit number I. Then you can think that, oh, it's the same, right? Actually, in order to calculate the carry out, then we require carry in. Then how can we reduce the delay of is multi-bit adder? So you know, so as I mentioned, in order to generate the carry out, so we require carry in. So which means that the carry is to be propagated from the previous digit to the next digit. But actually, I will show the final result. So actually, what the purpose of this carry required is to generate carry out early. So which means that actually by combining the carry propagation and then carry generation signal for each digit, then this carry required logic can generate the carry out earlier. So it may require the C in also, but so actually this logic can generate this T3 earlier than the ripple carrier. And let's see how. So that is actually the main purpose of the carry required adder. And then let's see how we can generate the carry out of the earlier. Okay, so this is the example. So this is for each column or each digit. Then we can define the propagated signal and then generate the signal like this. Okay, so for each digit. So you know, so this is the 4-bit addition. So for the addition for the A3 down to 0 and then B3 down to 0. And then only using A and B, so which means A and B, so A and B. So we can calculate the propagation and generation signal for each digit and P0, P1, P2, P3, and then G0, G1, G2, G3. And it's the same. So in this example, that is the 1011 plus the 0110, right? And then in this case, the propagation signal for each digit is 1, right? So all propagation signals are 1. So 1, 1, 1, 1. And then for the generation signal, so 0, 1, 0, 0. Then what can you observe for this propagation and generation signal? First of all, this example is the 1011 plus 01001, right? It's another addition. And then if we just calculate the propagation and generation signals for each digit, then it's the 1011 and then 001. Then what can we observe? Actually, for this addition, actually this addition is not the orbit addition, but better certainty is R part of multi-bit addition. So it means that we can consider the carry in or carry out of this 4-bit addition. Okay, so it means that if we just consider the carry, so that I mentioned that, so we assume that this 4-bit addition is the part of multi-bit addition. So for example, that this addition is the part of 64-bit addition. So in this case, this 4-bit addition can be still carried in, right? Because that can be the part of the multi-bit addition, for example, or some kind of this location. Okay? So in this case, so we can consider the carry in for this add operation. Like we can define C minus 1 and then C3. C3 is the carry out of this addition. So this is the thing. You can also define the C minus 1 and then C3. Then what can we observe? So in this addition, if the carry in, for example, if the C minus 1 is 1, because all carry propagation bits are 1 for this addition, and which means that the carry in, the C minus 1 will be propagated. Here the carry out will be propagated to carry out the last carry out. So which means that if the carry in is carry C minus 1 is 1, then this 1 will be propagated here the carry out. So actually, if we just speed up this propagation, then you can just observe that this carry in, the first carry in will be propagated through each bit. Okay. Then how about the generation? So actually we already know that. So in order to generate the carry out, actually the carry out is defined as the GI plus PI and CI. So actually we don't know. So we don't know the exact value of the C out without knowing the PI and CI, right? We just know that if the GI is 1, then CI is always 1. Okay? But in this case, so G3. So G3 is already G3 is 1. So which means that we can know just for this example, the carry out is always 1, even though the carry in is 0. Also, how about the propagation? The propagation, I explained that the carry will be propagated into next visit through each intermediate visit of this addition. So which means that if the carry is here, then we can check the propagation bit here, or propagate and carry will be propagate. Or is it propagation bit is 1? Then carry will be propagate. So what does that mean? But in this case, in this example, if we check the each propagation bit of this addition, then we can find the propagation bit is 0 for this visit. So which means that the propagation can be stopped. So what can we observe? What can we explain this propagation property? So in order to propagate the carry in into the next, the final carry out bit, then all bits of this propagation bits need to be 1. It means we can just consider the propagation of this group of addition, right? Then we can define the propagation of this group of addition is the end of each propagation bit, as I explained. Understand? So in order to propagate carry into next digit, then this carry propagation is performed to each digit, right? Then in order to propagate this C minus 1 into C3, then all propagation bits need to be 1, right? For this case, you can find the 0 here, then propagation is stopped at this point. So which means we can define. So actually for this example, we just define the propagation for each digit, but we can also define propagation for this block, okay, by combining the propagation of each digit. So this is the example. So I said that for this 4-bit block, so we can define the block propagation signal. Okay, so which means that we can just consider this is the block of add operation, and then this block add operation can receive carry in, and then it can generate the carry out. And then for the propagation signal, so we can define the propagation for this block is the end of all propagation bits. You understand? It's obvious, right? The carry will propagate. But if the one of the bit is 0, then the propagation is stopped. It is blocked. So the propagation for this block is the end operation of all propagation bits. Okay, we can define P3 down to 0. That is the block propagation signal. So we can define the block propagation signal is the P3 and P2 and P1 and P0. So we can define the block propagation signal. Then how about the generation? The generation is a little bit complex. It is because, so this is the block propagation. The propagation is easy to understand because I explained that the carry needs to be propagated via each digit. But generation is a little bit tricky. Why? It is because when we consider the generation, then we also need to consider the propagation. So what does that mean? So actually, the carry out for each digit can be generated using generation signal and propagation signal. And actually for it inside of this block, the generation is also determined by this carry in. Also the propagation of the carry in. So which means that if the carry is propagated from the previous digit, then this digit can generate carry, right? If the A is 1 and C in is 1, then we know that the carry will be generated. Understand? So actually, the block generation signal, is defined like this. So we can understand the block generation signal like this. So how the block, the carry out of this block will be generated. Is it generated? So if we just observe the last bit of block generation signal. So if the G3 is 1, which means the carry out is always 1, right? Right. And then for this block generation, so the column 3, the carry is generated if the generation signal for this column 3 is 1. And if the column number 2 is generate the carry, and the carry is propagated to the column 3, right? Then we can know that this block will generate carry out. So you can like this, you can think like this. So if we just consider this digit, the last digit, so we can know that for this, the carry out will be generated if the G3 is 1, right? So if the 1, this G3 is not 1 for this example, but if the A is for this A3 is 1 and B3 is 1, then carry out for this block will be always generated, right? So if the G3 is 1, then the carry will be generated. Or the carry can be propagated from the previous digit. Okay? So which means that the column 2 generates the carry, right? And then the column 2 generates the carry, right? The G2. And then if this carry is propagated in this bit number 3, understand? So carry is generated from previous digit, and then for this digit, the bit number 3, the carry will be propagated. So in this case, then we can know that the carry will be generated. Because the carry is generated from column 2, so bit number 2, then this carry is propagated. Then we can say that the carry is generated for each block. Also another case, carry is generated at column number 1, is a bit number 1, and then is propagated until the bit number 3. And carry is generated in number 0, and in number 0, and then it's propagated. So we can understand that the carry generation for this block, the 3 down to 0, can be defined like this. So if you see this equation, the Boolean equation, so we can understand that for the carry out, the carry generation for this block, we can define that carry is generated. Carry is generated the bit number 3, or the carry can be generated. Carry can be generated, and this carry is propagated in 3. The carry can be generated in number 1. Then this carry generated carry is propagated in number 3 into B3. And then the generated in number 0, then is generated carry is propagated. For this equation, we cannot find any carry in input, right? Because as I mentioned, this is the generation signal. So, I know this is a little bit tricky sometimes, but you can just understand that when we just consider the generation signal for this block, we do not consider carry in for this block, which means that the carry is generated inside of this block. The block generation represents the carry generation inside of the block. So which means that the carry can be generated by each digit, this digit, this digit, this digit, this digit, this digit, this digit, and this digit, right? And then also the carry can be, the generated carry can be propagated in the MSB. So this the last is that is the definition of carry generation signal for this block. So as I mentioned, we can understand the block generation signal like this. So carry can be generated inside of this block. So the carry can be generated by column number 3 and digit number 3, or it is generated from digit number 2 and then propagate. Okay, understand? So propagation is a little bit easy to understand because the carry is just propagate from carry in the carry out of the display. So that is the end operation. So propagate, 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 and propagate. So you can understand that block generation, that the carry is just generated inside of a block. Okay, and then we can define this block generation signal like this. So you can find that for this block generation signal, you can find the generation signal for each speed, G3 or G2, H1, and G0. Also, you can find the propagation signal for each speed, P3, P1, P2, P3, P1, P2, P2. Okay. So why do we learn this? Because so this is the example. So actually, if we just consider this block generation signal, then we can by combining, so it's the generation signal for each speed, then we can calculate the block generation signal like this. Okay, so you can find that this is the two-level and OR operation. Okay. What is different? And then actually this is the, so we can redefine the block propagation signal P3 down to 0 like here. Okay, and then block generation signal G3 down to 0 like this. And then for this block, we can define the carry out for this block is a C3, right? C3 is the block generation or block propagation and C in. Okay, so which means that for this 4-bit block, then we can generate C3 by combining block propagation. This is the 4 input and operation, and then block generation. This is the 2-level and OR and OR operation. So, what is the benefit? The benefit is we can quickly calculate the C3 by using block propagation signal with 1 level 4 input and and then block generation signal. It's a two level and O operation. And then by combining carry in, and you can generate the carry out of this T3 block very quickly. So it's faster than the block, faster than the ripple carry error. Right. So in order to for the ripple carry error, actually in order to calculate the C out, so this is the two level and O operation. So by doing this, then we can calculate the C out. And then this operation is added for each digit, right? So it looks like this. This is the AND operation and OR operation. And then this operation is just ANDed, and then it's OR again, and then ANDed, and then OR again for each digit. So in order to calculate this 4-bit carry out, then we require A level and OR operations, right? But in order to calculate the carry out for this 4-bit block add operation, we just require two level and OR operation and additional one level, additional two level. This is the one level. So additional one level OR operation. You understand? For the ripple carry error, we just require multi-level. So multiple two-level and OR operation. But for this carry required error, by defining block propagation and block generation signal, then we can generate the block propagation and block generation two-level and the OR operation. And then this is the one level and operation. And then so this is the also another and using the carry in. So which means it's just the one level and operation, 5 input and operation. So and then two level plus OR additional OR operation. Oh, it's actually we can just implement this is the two level operation. So the final is the also the OR operation, which means the 5 input or the final gate. So it looks like this. Let's do the block gate. Okay. So actually it looks like this. So we can generate the generation signal like this, and then also the propagation signal like this, and then we can quickly calculate the out signal. Okay. So this is the implementation of the carry required adder. So carry required has the propagation and then generation signal part for each digit, for each column, and then this column generates the carry propagation and then carry generation signal, and then this propagation and then generation signal is provided to the carry required loss. So you can find the P0 G0 and P1 G1, P2 G2 for each digit. So using the AND gate and OR gate, we can calculate each propagation and then and generation signal for each digit in parallel. And then this propagation and generation signal is providing the carry required logic, and by combining carry input for this block and then carry required logic inside of the carry required logic generate the G3 down to 0 and then P3 down to 0 by using propagation and then generation signal from each digit. And then by combining carry in and then G3 down to 0 and P3 down to 0, into is generated. This is the implementation of the carry required adder. Okay. So this is the carry required logic. Okay, so you can find this signal here. So and then this is the mechanism of the carry required addition. So there are two steps. And then actually this the mechanism, just to summarize the operations of carry required adder. So let's see the step one. Step one is the compute the GI and PI for each column or each digit. So actually, as I mentioned, PI and GI can be calculated in parallel. So this is in parallel, so which means that we just consume one logic gate delay, right? And then, so for this carry required adder, so the carry required logic received so this is the block carry required logic. So actually we just put multiple bits in the block. So block of carry required adder. So for each block, then the block generate the block propagation and then block generation signal by using the generation and propagation signal for each digit, right? Like this equation. So this is, so actually we do not use this equation because we just use the G3 plus P3 G2 and then P3 P2 G1 like this. Okay, we just want to use the two level logic gate. And so this is the example. So and then this block, a single block of carry required adder is generate the carry out signal for this block, right? And then this carry out signal is calculated quickly. Okay, so it means that this block, the carry out of this block need to be propagated into the next block. Okay, here. So actually, so we can just connect the carry out of this block to the carry in of the next block, and then also the repeating. Okay, so the carry is propagated for each block, propagated via each block of carry required adder. Okay, here, then the final result will be generated. Okay, so this is the delay computation of carry required adder. So what is different? Actually, the carry required carry adder ICA. Then the delay of carry required adder is proportional to the number of bits, and then this delay is multiplied by delay of full adder, right? And then when we calculate the purpose of carry required adder is to calculate the carry out of this block, the multi-bit block, more quickly. So we just divide the multi-bit addition of this adder into the multiple blocks, multiple k-bit blocks. Okay, so let us assume that this is the delay of n bits. We just calculate the delay of n bit carry over and then the each block includes the k-bit addition. Okay, so in order to calculate the delay of the carry required adder, then firstly each bit needs to generate the carry generation and propagation signal. Okay, so actually the PPG is the delay. The delay to generate the propagation and generation signal for each input. Okay, and then also for each block, we need to calculate the block propagation and block generation signal. So that will also take some delays. Okay, so this is the delay to generate all block propagation and all block generation signal. But fortunately, we can calculate the bit propagation and block bit generation in parallel. Also, we can calculate the block propagation and then block generation in parallel for each block. Okay, it's just adding the PPG is added and PPG block because we can calculate this block generation and the block propagation for in parallel for each block. And but in the carry required adder, so it just don't stop. The carry for each block needs to be propagated. Right. Right. So the carry, this is the number of required block for this carry required adder, n divided by k minus 1. And then for this, actually, the C out is the P I down to 0 plus G I down to 0 and C in, right? So that is so in order to calculate this carry out, and then for each block, then we also combine the block propagation and block generation. So this n divided by k minus 1 is the required block for this carry required adder. Actually, different block, but in order to calculate the delay, and actually n minus n divided by k is the required block, but the last block is removed from the delay calculation. So in order to generate the carry out, then also this carry out is propagated the last block. So this is the delay, and then this is the after the C, the carry is generated in each block, then using this carry, then we need to perform the full adder operation, right? Like this. So we also need to calculate the sum using the C2, C1, C0 generated from this carry required logic. Okay. So this is the delay of the carry required logic. Actually, compared to the delay of the different carry adder, this is a little bit tricky, right? So it's more difficult, but actually you can reduce the delay of carry generation, actually the delay of the carry out operation for each block. So by doing this, you can reduce the delay of adder. So usually the n-bit carry required adder is generally faster than the ripple carry adder if the number of bits is larger than 16. Okay, so usually the carry required header is faster. So this is the carry required header. So you can understand that for this carry required header, the main idea is that we can define the carry propagation and then carry generation for each block. And then if we can define the carry propagation and carry generation for each block faster, then using the carry in for each block, we can generate carry out faster than the ripple carry adder. That is the main idea of carry required adder. Okay, so I hope everyone can understand the mechanism of carry required adder. And then another adder design is the prefix adder. But then, what is the problem? What is the problem of carry required adder? The problem is that even though we can calculate the block, the delay of each block, so which means that if we can calculate the carry out for each block faster, then the carry is propagated through each block, right? So which means that actually the delay of the ripple carry adder is proportional. It's proportional to the n, but the delay of this carry required adder is proportional to the n divided by k. So actually we frequently use big O notation for comparing the complexity of algorithm, and we can say that the delay of ripple carry adder is the big O and n, but actually the delay of the carry required is also big O of n, because this n divided by k, right? So this is just n. So you know, we can just reduce the carry generated, carry out for each block, the delay of carry out for each block, and then also we can reduce the entire delay for this adder operation using the carry required adder, but the complexity is the same, the big O of n. So actually the carry, so you need to remember that the carry needs to be propagated through each block. Okay, that is the problem. So, but if we can reduce the delay, like the delay of n into the log scale, then we can reduce the delay. Well, we can reduce complexity actually if n is large. Okay, so that is the idea of prefix adder. So this is the carry ripple carry adder. This is carry required adder. As I mentioned, this is ON, and this is the ON, actually ON divided by K. But the problem is that also if the n is large, then the carry is propagated via each block. That is the problem of carry required adder. But the prefix adder also utilize the carry propagation and carry generation scheme. But when this block is, so actually when we implement the carry required adder, we define adder block, and then each block occupies the k-bit addition. So instead of this, we define the block size like the 1, 2, 4, 8, the power of 2, by receiving the result from the smaller block. So as you can see, you can find that the number is the power of 2 each log scale, right? So 1, 2, 4, 8. So the main idea means that we can, so actually for the CLA, we just define the k-bit block. But actually we can quickly calculate the carry out of this k-bit block using the carry required adder. But the problem is that the delay is accumulated. So delay is proportional because the carry needs to be propagated to the same size of block. But if we can generate the 1 bit and then next the 2 bit and then 4 bit and then 8 bit block using the output of this smaller block, we can reduce this number of stages. That is the main idea of prefix adder. So actually the main idea is of prefix adder is the same to the main idea of carry required adder. So which means that for each digit, so for each column, we just define the propagation bit and then generation bit, right? It's the same. In the carry required adder, we just define the carry generation and then carry propagation, and then by combining, then we just generate the block propagation and block generation, right? But when this block is generated, we can generate the block propagation and generation with the multiple stage. Then the size of the block is increased by power of 2. That is the main idea of a prefix adder. So let's see the example. So this is the implementation of the prefix adder. So what you can see, so you can find the digit number and digit number 0 to 15, the 16-bit prefix adder. And then this is the actually block propagation and block generation block. Okay. So as you can see, by combining 0 and -1, so I will explain later what this is -1. By combining these 2 bits, then we can generate the block propagation and block generation for this block. Block includes the bit number -1 to 0. Also, this is same. By combining these 2 bits, we can generate the block propagation and block generation. So actually, the first block just includes is only 2 bits, and then the next block. So the next block, then we can include the signal, the output from. So in order to generate the 2 down to -1, then we require the 2 down to 1 and then 1 down to -1 here. So by combining the block propagation and then generation signal from the higher level block, we can generate the low level block propagation and generation block here. Then so we can generate here, and then we can generate the block propagation and then block generation signal for each digit. Then we can generate by combining the block propagation and block generation, we can generate some signal. That is the prefix adder. Okay, let's see the example. So for the prefix adder, we just define the column -1. So you can say, oh, what is -1? So actually, this is the adder and this is hardware. So which means that -1 is unreal. It's the unreal bit because the bit number starts from 0. Then what is -1? So we can define the -1 bit like the carry in of this adder. So we can just think that this is the -1 bit, but A -1 is 0, B -1 is 0. And then the C in is just carry. Okay. So actually for this -1, we can just define that because this is the carry generation. But you know, if the carry in is 1, and it means that the carry is generated from -1 bit, right? And then actually the A and 0 is 0, and P -1 is no 0, right? So this G -1 is carried in, and then the propagation is the P -1, but it's 0. So, and then actually when we learn about the carry Lookahead adder, then we define the P I down to J is the block propagation, and then G I down to J. Okay, but you know the P I down to J is the P I -1, and then P J. And then we can also generate the G I down to J using the propagation bit and propagation and the generation signal for each column. So then, how about the P I -1 -1? If we just define this is the P -1, this is 0. So actually the P I -1 -1 is 0, right? Because the P -1 is 0. So the block propagation generated, then we just add all propagations from its digit, right? And then the C I -1 is the G I -1 -1. So we can define the block propagation and block generation like this. And actually you can find that the carry in to column I, the digit number I is same to the block generation I -1 and 2 -1. Okay. So and then which means that if we can quickly compute these generation bit, and then generation bit starts from the pin number -1, then which means we can calculate the carry very quickly. Okay, because the C I -1 is equal to G I -1 and -1. And then we already know that by combining some generation and then propagation bit, we can calculate the block generation and block propagation. Okay, so this is the equation. So which means the equation is that for the upper part. So actually we can generate the block generation using which means that this is the I down to K, and then K -1 down to some J. Then by combining block propagation and the block generation signal, then we can calculate the block generation and block propagation signal for the larger block. Okay, this is the main equation of the prefix adder. Okay, so J. So it means we can recursively generate the propagation and then generation signal for the every block, and then this propagation generation block can be started from the -1. Okay, so and then we just increase the size of the block like this, and then by doing this we can define the block propagation generation, and then by combining. So this is it actually we can calculate the carry of this digit, each digit. How? So as you can see, 0 down to -1 is the carry in for the C0, pin number 0. 1 down to -1 is the carry in of this digit. 2 down to -1 is the same. This is the carry in for this digit. So by combining this multiple propaganda and generator B, then we can calculate the G generation G0 down to -1, 1 -1, so 2 down to -1. But I explained that this is G0 down to -1 or -1 is same to the carry in for this digit, right? So if we can calculate the generation B, generation signal for this digit, then we know the carry in over this digit, and then calculate the sum of this adder. So this is the idea of prefix adder, right? So prefix adder, the main idea is that we can calculate the block propagation and block generation recursively by combining smaller block. Then we just define the -1, T0 and G0. And then we already know, we can know that I down -1 is equal to carry in of the ith bit. So if we just quickly calculate the generation of this I down to -1, then we can calculate the carry in quickly. Then we can quickly calculate the multi-bit addition. That is the prefix add operation, add idea. So I hope you can just check some operation after this prefix adder. It can be also a little bit tricky, but if you can understand, then it's recursively calculated. So if you can understand, I believe you can also understand the mechanism of the prefix adder. Okay, so this is the delay. So this is delay, and then so this is the example. So let us assume that the 2 input delay is the 100 per second and 2 adder is the 300. And then for the 3-pin add operation, the refractory add delay is the 9.6 nanoseconds. 1.2. Okay, so as n is large, and prefix adder is estimator carry equal data. Right? The n is large. That is the power. Actually, the power of log n big O over log n. So we can automatically reduce the complexity or some calculation if we use the big O over log n algorithm. Okay? The n is large. So okay, so I will stop here. And then I hope you can understand the mechanism of this carry for the prefix adder. Okay. Any question? Thank you for attention. See you in the next class.